For today, we'll be looking at another different variant of paper 1. We'll be looking at June 2022 P12. Okay, so have a look at the first question. The first question is asking you which of the following estimate is reasonable. In the first one, we have 1 times 10 power minus 3 kg for the mass of a grain of sand. So if we have sand right over here right now, the question is actually saying that the mass of 1 grain is 1 times 10 power minus 3 kg, which in turn is 1 grams. So you try to imagine a little, this would mean that 100 grains of sand would be 100 grams, and then 1,000 grains of sand would be 1,000 grams, which is then equals to 1 kg. If you were to take 1 teaspoon and you scoop out the sand, the amount of sand that you have inside would definitely be more than 1,000 grains. Does this mean that you would be scooping out sand that is more than 1 kg? Now, I'm sure you already have some idea of how much 1 kg is from your normal everyday experience. So if you imagine yourself taking a teaspoon and then scooping out a grain of sand, can it even be more than 1 kg? It isn't reasonable, isn't it? So this one is definitely out. Okay, so A is out. And then the next one, we have 1 times 10 power minus 2 meter cube for the volume of a tennis ball. Now this one, we can make a reasonable estimate. Let's just assume that our tennis ball is something like this. And if you take a ruler, you can roughly guess what's the size or rather the diameter of a tennis ball. The diameter of your tennis ball will probably be hovering around, say, 7 centimeter. So that your radius is actually going to be half of that value. The radius will be 3.5 centimeter. So now what you want to do is you calculate out the volume of your tennis ball. Volume of a sphere is 4 over 3 pi r cubed. So you sub in the values right now for the radius of 0.035 meter. Don't forget to cube it. You will be getting a value of 1.80 times 10 power minus 4 meter cube. Now, in your case, the question says it is supposed to be equal to 1 times 10 power minus 2 meter cube. So is this even comparable in the first place? This one is not even comparable in the first place because you see the power of 10 is completely different. This is 10 power minus 4, this is 10 power minus 2. So this is out. So number 2 will be out of the question too. Now, if you then look at D, which is the last one, 1 times 10 power 4 watts for the power of a light bulb in a house. Now, if you are talking about light bulb, which basically is something that looks like this, if you had the opportunity to walk in the mall and then you've walked through the lighting sections, you notice that in terms of the wattage of the light bulbs that are sold there, you very seldom will see the power of the light bulb exceeding 100 watts. 100 watts is probably the highest it can go. Okay, so right now, your question is saying that the power of your light bulb is 1 times 10 power 4 watts, which is actually 10,000 watts. This is definitely too high. Okay, it's not comparable right now. So if you compare 100 watts with 10,000 watts, this is a very big difference. So answer D would also be wrong. Okay, so that leaves you with just answer choice C. So let's check whether this one would be correct. You have 1 times 10 power 0 joules for the work done in lifting an apple from waist height to head height. So let's imagine this right now. You have a person, sorry, I used a wrong pen. You have a person like this. The question is saying that you're lifting an apple. Let's call this your apple here. you're lifting it from waist height to head height. So imagine that your waist height is here, and then your head height is here. So the distance between your waist and your head would probably be about 0.5 meter, about 50 centimeter. And then when you're talking about the mass of your apple, the mass of your apple could probably be 0.5 kg. So what is the amount of work that will be done in order to lift this apple from your waist to your head level? So the work done here can be calculated from this. The work done can be assumed to be equal to the change in your GPE, which in turn is equal to mg delta h. So if you sub in the values now, you get 0.5 times 9.81 times 0.5. You will get a value of, say, 2.5 joules. The question is saying that your work done is 1 times 10 power 0 joules. Is actually equals to 1 joules. So if you now make a comparison between these two is actually quite comparable. One of them is 1 joule, then the other is 2.5 joules. In terms of power of 10, they are actually the same. So you would actually say that this is actually a reasonable estimate. The answer for this is C. All right. Now in question 2, what is the symbol for the SI base unit of temperature? They want the SI base unit, okay? So from what you've learned from chapter 1, you could easily answer this as B, Kelvin. Now answer D is wrong because it has the symbol of degree here. When you want to quote your temperature in Kelvin, it's just Kelvin. It's not degree Kelvin, okay? So that's why D here is out. And needless to say, if you're trying to state your temperature in degrees Celsius, this would also be wrong. Those aren't SI base unit. SI base unit, strictly speaking, is just Kelvin. All right. Now, for the third question, this one, which statement about systematic errors is not correct? You want to find the statement that is not correct here. So in our case, if you look at A, a systematic error can be caused by using an incorrectly calibrated instrument. So an incorrectly calibrated instrument could probably give you, for example, 0 error. So 0 error is actually one of the causes of systematic error. So answer A is actually a correct statement. Then how about answer B? For answer B, they mentioned that one particular type of systematic error can affect all the measurements by the same amount. So if you recall, what is the definition of systematic error? Systematic error results in readings that are always either above or below the true value. Okay, systematic error will always result in readings that are above or below. Only one of them. It cannot be a mix. All right. So here, when they say one particular type of systematic error can affect all the measurements by the same amount, this one is actually true. In this sense, it could mean that all your readings are always above your true value. Or it could also mean the converse. All your readings are below the true value. Okay, so B is a correct statement here. And then if you look at D, 0 error is the type of systematic error. This is actually what we just discussed in A. 0 error is actually a type of systematic error. Okay, it causes systematic error. So answer D is also a correct statement. So that means the only incorrect statement here will be C. But let's check it. The effect of a systematic error can be reduced by repeating and averaging the measurements. So here they're telling you systematic error can be reduced. This is actually wrong. One of the things that you learn about systematic error is that systematic error can be eliminated. It can be eliminated, but not reduce. Okay, so even if you to take repeated readings and then averaging it, it will not reduce your systematic error. So answer choice C is the wrong statement. It is the answer that you want right over here. Okay. In question 4, an object is moving with an initial velocity of 4 meters per second to the right. The velocity of the object changes so that its final velocity is 3 meters per second downwards, as shown here. Now, this is your initial velocity moving towards the right at 4 meters per second. And then this one is your final velocity moving downwards at 3 meters per second. Which arrow below here represents the change in velocity of the object? Now, you need to pay attention to what they're trying to find out here. They're trying to find out the change in velocity. It is not asking you to find the resultant velocity. Change in velocity and resultant velocity are two different things. Most of your questions that you've done so far is about you finding the resultant velocity, the resultant vector. This one in particular is asking you for something that is different. They're asking you to find the change in velocity or the change in the vector. So let's just review how to define change in vector and resultant vector. So the first one you will have learned before this is to find resultant vector, you will first need to draw the vectors from head to tail. Okay, and then after that, the resultant vector is represented by any gap that you see remaining. Okay, where from there we will say that the length of gap is the magnitude of your resultant vector, and then after that the direction of your resultant vector is from initial to final point. So let's just apply it to our question here. We have an initial velocity of 4 meters per second going towards the right, followed by a final velocity of 3 meters per second going downwards. So we draw the vectors from head to tail in this manner. This one is our initial vector at 4 meters per second. This one is our final vector at 3 meters per second. So notice that there's a gap remaining here, indicated by this red line here. So the length of this gap will be our magnitude of the resultant vector, and the direction will be from our initial point to our final point. We can say that this is our initial point because we started drawing from here, and then this is our final point because we ended our drawing here. So our resultant would actually be something like this. Okay, now if we want to find out the magnitude of the resultant vector, notice that this is actually a right angle triangle. We can actually use Pythagoras theorem to find out the magnitude of our resultant vector here, which in our case, the resultant velocity will be 3 squared plus 4 squared, giving me 5 meters per second. Okay, so this is something that we've learned in chapter 1. The one that we never really did do much was to find vector change. So in our case, to find vector change, you need to draw the vectors starting from same point. Okay, you need to draw the vectors starting from the same point. You don't draw it from head to tail. All right. So after you've drawn the vectors starting from the same point, the vector change is represented by any gap remaining, where in our case, the length of gap is the magnitude of the vector change. And then after that, the direction of the vector change is from the initial to final vector. Okay, so let's apply it to our question here. We draw the initial vector starting from one point here, and then we draw the final vector starting from the same point too, like this. Okay, so this one is our initial vector at 4 meters per second. This one is our final vector at 3 meters per second. You again see that there's actually a gap here. So as mentioned, the vector change is represented by any gap remaining. The length of the gap will be representing the magnitude of your vector change, and the direction of your vector change will be from your initial to your final vector. So in our case, the vector change is represented by this pink arrow like this. Okay, so this is our vector change. Now, if you want to find out the magnitude of the vector change, you will again notice that this is a right angle triangle. You can actually use Pythagoras theorem to find out the magnitude of the resultant. So this one will be square root of 3 squared plus 4 squared, giving you 5 meters per second. Okay, so there's something here that you can draw a conclusion from. You notice that the resultant vector is 5 meters per second. The vector change or velocity change is also 5 meters per second. Magnitude wise, they are the same. But in terms of the direction, notice that my resultant velocity or my resultant vector is going diagonally downwards towards the right, whereas my velocity change or my vector change is also going diagonally downwards but towards the left. Okay, they are actually 90 degrees to each other. Okay, from the two diagrams that have been drawn, there's two conclusions that we can draw from them. The first one is in terms of the magnitude. We can actually say that the resultant vector is going to be the same as vector change in terms of magnitude. In our case, we can actually say that resultant velocity is the same as change in velocity in terms of the magnitude, because you can see here, this one is 5 meters per second, this one is also 5 meters per second. And then what can you then say about the direction? As for the direction, we will say that resultant vector is always perpendicular to the vector change. Okay, in our case, again, the resultant vector is our resultant velocity, and the vector change here is our change in velocity. So to answer the question that has been asked here, we are supposed to find out the change in velocity of the object. The change in velocity of the object is actually represented by this arrow here. So our answer is supposed to be B. Okay. Now, if you're asked to find out the resultant velocity would actually be in this direction. Okay. This one will be our resultant velocity, and it will be at 90 degrees to our velocity change. Okay, so this is just some things to note about resultant vector and velocity change. For question 5, a car travels anti-clockwise along a horizontal circular road of radius 12 meters as shown. The car takes a time of 4 seconds to move from position P to position Q. What is the magnitude of the average velocity of the car for the journey from P to Q? So we have a car that moves from position P to position Q here after having moved counterclockwise along a circular path. The question wants us to find average velocity. Bear in mind, they are not asking us to find average speed. Average speed and average velocity are two different things. So if we are talking about, say, average velocity, it is defined as total displacement divided by total time. Now we know the total time as 4 seconds, but we need to find out what is our total displacement. So if you recall what's the definition of displacement, displacement is actually the distance from a reference point in a specific direction, or in other words, it's actually the straight line distance between 2 points. So in our case, the displacement between P and Q is actually this red line here. And the direction will be from our initial point to our final point. So we're pointing downwards. This is our displacement. So from there, you will also be able to notice that there's actually a right angle triangle right over here. So we know it's 12 meters here. It should also be 12 meters here. From there, we will be able to use Pythagoras theorem to find out what is our total displacement. It will be 12 square plus 12 square, giving us 16.97 meters. So if we put this value into our equation for average velocity, we ought to get 16.97 divided by 4.0, giving us an answer of 4.2 meter per second. This one will be our average velocity. But let's just say we are interested to find out our average speed. How would this working be? If we are asking for average speed, we need to find total distance divided by total time. So if we are being asked for total distance now, total distance by right should actually be indicated by this. It will be from here going all the way to here. Okay, notice that it's actually 3/4 of the circumference of a circle. This blue line here is our total distance. It's actually 3/4 of the circumference of your circle. So if this one is 3/4 of the circumference of your circle, it will actually be 3/4 pi r squared. So if we sub the values in to our equation now, total distance is 3/4 pi r squared. Our radius is 12 meters. Square that, divide by 4.0 seconds. We will eventually get the final answer as 14.1 meter per second. Okay, this one would be our average speed here. So in our question, this one here, 14.1 meter per second, would have actually been our average speed. Okay, but our question wants average velocity, not average speed. All right. Now in question 6, the water surface in the deep well is 78 meters below the top of the well. A person at the top of the well drops a heavy stone down the well. Air resistance is negligible. The speed of sound in the air is 330 meters per second. And then from here, what's the time interval between the person dropping the stone and hearing it hitting the water? So in the first place, air resistance is negligible here. From here, we will know that weight is the only force. From there, we can conclude two things. A will be equals to G, and A is constant right over here. So to get a better appreciation of what this question is about, we better just draw out a simple diagram. So in our case, we have a person standing right over a well, and then the well has some water right over here. It was mentioned to you that the well is in the first place 78 meters deep. Okay, so this well here is 78 meters deep. Let me just draw it out for you. This well is 78 meters deep. So we have a person that's right over here, and he dropped a stone down. So the stone is probably this one. It's moving downwards like this, until it hits the water surface with a splash like this. Okay, so once your stone hits the water surface and makes a splash, it will emit sound waves. You will have sound waves that will travel from the bottom of the well to the top of the well, where the person will now hear the sound. So in our case, something will be rising back up. In our case, it's actually the sound wave. So we would have sound wave rising back up. So we will have the sound wave going up like this until it reaches the top of the well to be heard by the person. Okay, so now there's actually two motions to consider. The motion downwards will be considered as constant acceleration. This one is applied for the stone. And then there will be another motion outwards. This one will be considered as constant velocity. This one is applied for the sound wave. Okay, so we're interested to find out the time taken between dropping the stone and actually hearing it hitting the water. Okay, so we want to find out time t1 for the stone moving from the top of the well to the water. And we also want to find time t2 for the sound wave being emitted from the bottom of the well going all the way to the top of the well. So we need to split our analysis into two parts here. Let's just start for the case where we have constant acceleration. Now, because it's constant acceleration, we know that the kinematics equations would apply here. The kinematics equation, you have 4. V is equals to u plus at, s is equals to half u plus vt, s is equals to ut plus half at squared, and finally v squared is equals to u squared plus 2as. Okay, so let's just see what are the variables that we know in the first place for the case where the stone was being released to the point it hit the water at the bottom of the well. We can assume that our initial velocity is 0 because it was released from rest. The final velocity on hitting the water surface is not known for us. The time taken is also not known for us. The acceleration is equals to gravitational acceleration because the only force acting here is just the weight. And then as for our displacement, we already know it's 78 meters. So there are two unknowns here. The final velocity on hitting the water surface and the time taken to hit the water surface. So the time taken to hit the water surface is what we want to find out, whereas the final velocity on hitting the water is not what we want to know. So here, in order to select the suitable kinematics equation, we will just disregard any equation with the unwanted variable of v here. So here, the first equation will be out, second equation will be out, third equation will be in, fourth equation will be out. First, second, and fourth equation has the unwanted variable of final velocity inside, so we do not want that. We only want to use the third equation now. So if we apply the third equation, we must first set our sign convention. Because the object is moving downwards in the first place, downward is considered to be our initial sign convention. So s is equals to ut plus half at squared. S is 78, u is 0 plus half times 9.81 times t squared. So t here would actually be 3.99 seconds. This is our t1. Okay. Then if we apply the constant velocity case here for the sound wave, we would use the equation v is equals to s over t. So we already know that the speed of sound is 330. The displacement, the distance traveled by the sound wave all the way back to the top will be 78. And then t is what we want to find out. T will be 0.24 seconds. This would be T2. So right now we want to find out the time interval. What is the time interval now? In our case, the time interval, let me find a suitable color, probably green. Our time interval now is T1 plus T2, which will in turn mean 3.99 plus 0.24, giving us the final answer as 4.23 seconds. So our answer here is supposed to be D. Okay. In question 7, which statement is not a requirement of a pair of forces that obeys Newton's third law of motion? You are supposed to find out what is not an essential requirement here. Now, if you recall what was Newton's third law mentions this: when two bodies interact, they exert equal and opposite forces on each other. Okay, there are 4 conditions to satisfy here. The first one must be equal magnitude of force. Second one is opposite direction of force. The third one must be on opposing bodies or different bodies. And the fourth one must be same type of force. Same type of force here means that in the pair of forces, if one of them is a contact force, the other must be a contact force. If one of them is a gravitational force, the other must be a gravitational force. Or if the other is an electric force, the other must also be an electric force. Okay, that is what we mean by same type of force. So now if we look at the answer statements one by one, in A, the forces act in opposite directions. This is actually an essential requirement. And then in B, the forces act on different objects. This is also again an essential requirement. Just now I mentioned they must be acting on opposing bodies. And then if you look at answer choice D, where they say that the forces are of equal magnitude, this is again an essential requirement. So that leaves us with only answer choice C, where we say that the forces act on objects in contact. This is actually not an essential requirement for Newton's third law. Okay, you could have a case where the objects are not in contact and they still have Newton's third law being applied there. So for example, let me just try to draw a few cases. The most common example that you're used to seeing is, say, for example, you have a wall here, and then you have a person that is pushing hard against the wall like this. The person exerts a force on the wall, and in return, the wall exerts a force back on the person. This one is requiring contact for Newton's third law to apply. But there are also cases where you do not require contact for Newton's third law to apply. The easiest example I can give you is, say, for example, you have the Earth like this, and then you have an object somewhere in the air here. We know that the Earth will exert a gravitational pull on the object, and in return, the object will also exert an equal opposite gravitational pull on the Earth. So this one requires no contact. Okay, another different example I could give you is between charges. If you have a positive charge and a negative charge, the positive charge will be attracted to the negative charge, and likewise the negative charge will also be attracted to the positive charge due to Newton's third law. Again, this one has no contact. Okay, so for Newton's third law to apply, you do not necessarily need to have contact between the objects. All right. In question 8, a child of mass 20 kg stands on the rough surface of a sledge of mass 40 kg. the sledge can slide on a horizontal frictionless surface. One end of the rope is attached to the sledge. The rope passes around a fixed frictionless pole, and the other end of the rope is held by the child, as shown. The rope is horizontal. The child pulls on the rope with a horizontal force of 12 Newton. This causes the child and the sledge to move in equal acceleration towards the pole. What is the frictional force between the child and the sledge here? Now, for our current case, it will probably be better to separate out the diagram into 3 separate parts. So we have the child right over here, and then we have the sledge right over here. And lastly, we have the rope. One end is attached to the child, one end is attached to the sledge, as mentioned by this part of your question right over here. Okay. Now from there, it was further mentioned that the child pulls on the rope with a horizontal force of 12 Newton. Let's call this force T. Okay. So the child pulls on the rope with a force of T. Now when it concerns a cable, generally cable or rope, if you notice that the force acting on one end of the rope is like this, the other end of the rope would have a force equal and opposite to it. A similar case would apply if the forces were opposite in direction, meaning to say if you had a force like this, there will be an equal opposite force on the other end of the rope like this. So this question will be more on this case here, not the second one. So if you look at the rope itself, we already have a force of T here. The other end should have an equal and opposite force T here. These are the forces on the rope. Okay. From here, we are interested to find out what are the forces acting on both the child as well as the sledge. We would need to use Newton's third law here. Now, if you just focus your attention on the interaction between the child and the rope, the child is exerting a force T onto the rope. So according to Newton's third law, the rope will exert an equal opposite force of T back onto the child, like this. Now, the child would now start to move forward, but because he is standing on the rough surface of the sledge, there will be frictional force. Let's call this frictional force R. The frictional force will oppose the motion of the child forwards, so the frictional force must therefore be acting backwards. This is the frictional force acting on the child, okay? Then we look at the forces acting on the sledge. So if you look at the forces acting on the sledge, you first look at the interaction between the sledge and the rope. The sledge is exerting a force T on the rope. So according to Newton's third law, the rope will exert an equal opposite force back onto the sledge in this direction. Okay. And then from there, you look at the interaction between the child and the sledge. The sledge is exerting a frictional force on the child, which is directed backwards. So according to Newton's third law, the child will also exert an equal opposite force back onto the sledge in this manner. So there is a frictional force acting on the sledge in this direction here. So these are all the forces that are now currently acting on the child as well as the sledge. The question also further mentioned that the child and sledge move with equal acceleration. So that would have meant that for the child, he will be moving with acceleration A, and then for the sledge, it will also be moving with the same acceleration A. Now, to find this acceleration A, it will be more convenient to consider both child and sledge as a single system. So if now we say child and sledge as one system, the diagram that we would have, the free body diagram that we would have, would look something like this right now. Okay, so you have the horizontal force exerted on the child by the rope here, as well as the horizontal force exerted on the sledge by the rope here. Okay, now you won't need to consider the frictional forces, because if you consider the frictional forces on the child and the frictional force on the sledge, notice that they are actually cancelling each other off. So these two forces need not be considered. Okay, and also bearing in mind that there's also no frictional force between the sledge and the frictional surface on which it is sliding. Okay, so now if we apply the equation F net equals to MA right over here, we will actually have T plus T equals to the mass of the child plus mass of the sledge times A. So you start to sub in the values, you actually be 12 plus 12 equals to mass of the child being 20 kg, mass of the sledge being 60 kg. You will get the acceleration as 0.4 meter per second square. This is now the acceleration of the entire system, which is also the individual acceleration of the child as well as the sledge. Okay, now from there, you can now work out what are the frictional forces. So if you want to work out the frictional forces, you need to consider the forces individually on the child or the sledge. Okay, so I'll show you both examples here. So now if I just consider the free body diagram acting on the child itself, let's just call this the free body diagram of the child. We would have the child here, and you have the horizontal force T acting on the child of 12 newtons. You have an acceleration of A equals to 0.4 meter per second square. And then you also have that frictional force R, which is what you want to find. So here, if you again apply F net equals to MA for the child alone, we will actually say this. This one would be T minus R equals to the mass of the child times with A. So it will be 12 minus R equals to 20 times 0.4, giving you an R of 4 newtons. All right. Now, you could also equally apply your analysis on the sledge alone. So if you consider the free body diagram acting on the sledge, this is, say, your sledge. We have the horizontal force of T acting like this. Again, is 12 Newton. We have the frictional force acting on the sledge like this. And then we have our acceleration A of 0.4 meter per second square. So here, if you apply F net equals to MA, you will get T plus R equals to mass of the sledge times with A. So in our case, it is 12 plus R equals to 60 times 0.4. R would be 4 newtons. Okay, you're getting exactly the same answer as that if you were to consider the free body diagram of the child alone. Okay, so over here, your answer should be A. Okay, so it doesn't matter whether you consider the free body diagram of the child or free body diagram of the sledge, you actually will get back the same answer. You just need to pick one. In question 9, you have a stone S and foam rubber ball R that are identical spheres of equal volume. They are released from rest at time t equals to 0 and fall vertically through the air. Both of them reach terminal velocity. Which graph best shows you the variation with time t of the speed v of the stone and of the rubber ball? So let's just review a little on what we know about terminal velocity. Now, when you have something that falls with terminal velocity, air resistance must be present in order for it to eventually reach terminal velocity. So let's just assume that right now the sphere is what I just drew on the left-hand side here. So for this sphere, the forces that will be acting on it would be your weight, W, and your air resistance, R, that is opposing its motion. So your acceleration is directed downwards as your object is falling. Your net force would actually be equals to W minus R. So one of the things that we know is that air resistance is actually proportional to your speed. So in our case, as speed increases, air resistance will increase. So if you apply it to the case of something that's falling right now, what we can actually say is that your R increases so that your F net decreases, because you can see from here, F net being W minus R, the weight itself remains fixed. But if your air resistance is increasing with time, that would mean that your net force will drop. So when your net force drops, your acceleration would also decrease. So what would then happen is this: your air resistance continues increasing until it is equal to W. It is equal to the weight. So at this time then, what will happen is that your F net is 0, your A is 0, and your velocity is constant. This velocity that has become constant here is what you know as your terminal velocity. Okay, so one of the things to note about your velocity time graph for something that falls and achieves terminal velocity is that it should by right look something like this. If I were to draw for you a graph of velocity versus time, the general shape of the graph should look like this. I try to draw it as best I can. Just give me a moment. There will be one particular section where your velocity increases at a decreasing rate, and then there will be another section where your velocity becomes constant. Something like this. Okay, this is how your typical velocity time graph will look like. So there will be one portion here for your motion where we say velocity increases at decreasing rate. Okay, the velocity is still increasing, just that it isn't increasing as much as before. Okay, and then there will be one portion here where your velocity will become constant, this particular portion here. So this part here is where you achieve terminal velocity. Okay, so if you look at it another different way, if I were to split it out into two different parts, the first section here on the left will be where my acceleration is decreasing. The second section here is actually where my acceleration has reached 0. Okay, and from there I can also kind of make some comparison between the forces. On the left hand side here, my air resistance is actually still more than the weight. Okay, and then on the right hand side, once I've achieved terminal velocity, my air resistance is actually equals to the weight. Okay, so that's just some things to note for terminal velocity. Now let's just apply what we know to our question here. Looking at this question, you have two spheres made of two different materials. The first one is stone, the second one is rubber, and they are identical spheres of equal volume that are then released from rest at time t equals to 0 and fall vertically through the air until they both reach terminal velocity. So let's just consider the individual cases. You have stone, and then you have rubber. Okay, so let me just draw out the spheres for you. This one representing the stone, and then this one representing the rubber. Now, the forces that act on the stone would just be the weight of the stone and the air resistance. And then for the rubber, it will be the weight of the rubber and the air resistance. Okay, so we know that for both spheres to fall and achieve terminal velocity, the air resistance must continue increasing until it is equals to the weight. Now, in the first place, is there any difference in the weight between the stone and the rubber? You can say that there actually is a difference, because you can say that mass of the stone is more than the mass of the rubber, so that the weight of the stone would be more than the weight of the rubber. So in our case, let's just give some values to the weights. I could say that the weight of the stone is maybe 1,000 Newton, and the weight of the rubber is maybe say 10 Newton. So if you talk about the time taken for air resistance to increase until it's equals to the weight, which one would actually take a longer time? You will automatically say that it should be for the stone, right? R increases to equal W over a longer time. Let me just rewrite this. So this one will take a longer time. The converse will be true for the rubber ball. R increases to equal W over a shorter time. Okay, now the time that it took for R to increase until it's equals to W will actually affect the time you reach terminal velocity as well as the magnitude of terminal velocity that you reach. So let's just say, for example, I thought about the rubber. The rubber will reach terminal velocity earlier and at a lower magnitude. Whereas for the stone will reach terminal velocity later and at a higher magnitude. Okay, so you can probably appreciate why terminal velocity will be reached earlier for rubber and why is it later for stone. But how do you explain the magnitude part? It will be easier to look at it from the point of view of the stone. Why do I say that the terminal velocity reached for the stone will actually be higher here? It's because in the first place, you had a longer time to reach terminal velocity. Remember just now I mentioned to you here, your R will increase to equals to W over a longer time. So this one actually means this. There is longer time for stone to continue to speed up at a lesser rate. Okay. Therefore, its final terminal velocity is higher. Okay. Because there's a longer time for your stone to continue to speed up at a lesser rate, its final terminal velocity would therefore be higher. Okay. So if I wanted to draw a graph just to show you what I mean by all of this, I'll draw it right over here. This one is a graph of, say, velocity versus time. For the case of the rubber, it will probably look like this. Then suddenly it will achieve terminal velocity. So this is the time that it took to reach terminal velocity. Let's just call this TR. And then this is the terminal velocity reached. This is BR. But when it comes to the case of the stone, it could probably look like this. Okay, so my terminal velocity is reached at a much later time. Say this one is TS, and then my magnitude of my terminal velocity will be larger. So in other words, magnitude of terminal velocity for stone is going to be larger than that of rubber. And then the time taken to reach terminal velocity for stone will be larger than that for rubber. Okay, this is the graph that you expect to see. The one that is actually showing you that in your question is actually B. S here refers to stone, R here refers to rubber. Now, if you look at the time taken for both of them to reach terminal velocity, this one is the time taken for rubber to reach terminal velocity, and then this one is the time taken for stone to reach terminal velocity. As for the magnitude of the terminal velocities for the rubber, this is the magnitude. For the stone, this is the magnitude. You can see from here that this graph is exactly the same as this. All right. The rest of the answer choices are clearly different. Then for question 10, this one is your normal question on relative velocity. So two balls X and Y are moving towards each other with speeds of 5 meters per second and 15 meters per second respectively. They make a perfectly elastic head-on collision and ball Y moves to the right with a speed of 7 meters per second. What's the speed and direction of ball X after collision? This is actually one of the past years that has been repeating itself quite often if you've been doing your past year questions. So they told you that your collision here is perfectly elastic. Now, when you know that your collision is perfectly elastic or just elastic, there's usually two criteria that comes into play. The first one being saying that relative speed of approach is equals to relative speed of separation. Okay, and then the second one saying that kinetic energy is conserved. Total kinetic energy before collision is equals to total kinetic energy after collision. But we won't be using this second condition to evaluate this question. We will be using the first condition here. So when it comes to finding relative speed, this is the thing that you would have learned before this. To find relative speed, you really only need to look at two cases. Whether the objects move in same direction or opposite directions. So if they're moving in same direction, your relative speed is just simply the higher speed subtract off the lower speed. In other words, take the difference in speed. But when it comes to objects that are moving in opposite directions, your relative speed is going to be really just the higher speed plus lower speed. In other words, what you're just supposed to do here is just add up the speeds. Okay. So in your case, if you just look at your diagram here at the start of the question, this one here, you are trying to find the relative speed of approach. You try to find the relative speed of approach here. This one, you'll notice that both objects are moving towards each other. This is a case where they move in opposite directions. Okay. So you just add up the speeds together. In your case, this one will actually be 5 plus 15, giving you 20 meters per second. Okay. So after collision, what the question mentioned is that Y will be moving towards the right with a speed of 7 meters per second. So this one is already known to be moving 7 meters per second towards the right. So what you do not know now is X. X is the one that you do not know. You do not know the direction. You do not know the magnitude of the velocity. But what you do know is that because it's a perfectly elastic collision, the relative speed of separation must be equals to 20 meters per second. Okay, that's what you should be able to see here. So you evaluate each of the answer choices one by one. If you say that Y is moving 7 meters per second towards the right, and then X is moving 3 meters per second towards the left, this is a case where the objects move in opposite direction. So your relative speed of separation will just be 3 plus 7 equals to 10 meters per second. Then after that, if you evaluate for B, where Y moves again 7 meters per second, X moves 13 meters per second, it's still a case where they're both moving in opposite directions. So you just add up the speeds, giving you 13 plus 7, 20 meters per second. So this relative speed of separation is the same as relative speed of approach. This one ought to have been the answer. Okay, but let's just double confirm with the rest of the answer choices to see whether we're correct or not, because sometimes there may be some other tricks to the question. So if you evaluate C, where they tell you it's 7 meters per second towards the right, and then it is 3 meters per second towards the right also for x. The relative speed of separation here, because they're both moving in the same direction, you take the difference in the speed. Higher speed minus lower speed. So it will be 7 minus 3 equals to 4 meters per second. So this one is definitely out. And then after that, you evaluate again with some other answers here. This one, you have y moving 7 meters per second towards the right, x moving 30 meters per second towards the right. So again, they're both moving in the same direction. Take the difference in the speed. It will be 13 minus 7, giving you 6 meters per second. Okay, so none of these are actually the same as your relative speed approach. So C and D is out. A is also out. Only B was giving you the same relative speed approach. So answer is B. Okay. Now, then after that, if you move on to question 11, two forces form a couple. Which statement describes the two forces? Now, this one you will have to refer back to the definition of what is a couple. A couple is a pair of equal but opposite forces separated by distance. Okay, this is what a couple actually is. You need to have equal force, opposite force, and then there must be separation between them. So in other words, you are looking at something that looks like this. Okay, wait, this is not the correct arrow. You're looking at something that looks like this. This one is one force. This one is another force. This one is force F equal magnitude, but they're separated by a distance d. Okay, so you look at the answer statements here. They are in the same direction. This one is obviously out. They must be in opposite directions. They are perpendicular to each other. This one is also out. They are supposed to be parallel to each other. In other words, you see, when they are equal but opposite forces, this one also kind of means that they are parallel to each other. Okay. When you have them equal and opposite, specifically when you say them together like this, it really implies they must be parallel to each other. So you say them perpendicular, this is out. Then after that, they must have same magnitude. This one is what you want, right? This is one of the conditions for a couple. C should be the answer. Now, if you look at the last answer choice where they say they pass through the same point, this one is definitely out because they must be separated by distance in the first place. If you have a force F like this and then another F like this also, where they pass through the same point, there's no separation of distance between them. This one is not a couple because there's no separation between them. Okay, so that's for question 11. Now then you look at question 12. Question 12 is asking you, a uniform rod is attached by a hinge at one end to a wall. The other end of the rod is supported by a wire so that the rod is both horizontal and equilibrium. So keyword here is that this rod is in equilibrium. Which arrow shows the direction of the force on the rod from the hinge? So they're asking you about the force on the rod from the hinge itself. There's supposed to be some sort of force from the hinge onto the rod here. This is the force that they're talking about. But right now, they are specifically asking you, what is the direction of this force in the first place? So to do this question, just remember this. You try to identify all the forces. When they say this is uniform rod, that means weight X at the center of rod, right in the center. Okay, so I know that my weight is going to be right over here. This is weight W. And then because I have a wire attached to the rod, this wire here being attached to the rod, the wire will actually exert some sort of tension onto the rod itself. So the tension acting on the rod would be something like this. Okay, so from here, what you just need to do is you try to extrapolate the line of action of these two forces. You extrapolate the line of action of the weight. You extrapolate the line of action of the tension T. Let's call this tension T. You will notice that they tend to intersect at one point. So from here, you can actually then say that the force from the hinge on the rod must pass through this point here. Okay, so one thing that you might have learned last time was that for non-parallel forces in equilibrium, they must pass through a common intersection point. The common intersection point is actually this point here. Okay, so all the forces that are listed here, that are drawn on the diagram here, must pass through this point. So the force on the from the hinge on the rod, this blue colored arrow here, must pass through this point. So your answer here will actually be D. The rest of the answers would not be correct. Okay, so that's for 12. Then you move on to question 13. Okay, so question 13, let me just clear this one off. Now in question 13, they mention a diving board of length 5 meters is hinged at one end and supported 2 meters from this end by a spring or spring constant 10 kilonewton. A child of mass 40 kg stands at the far end of the board. What would be the extra compression of the spring caused by the child standing on the end of the board? Okay, so they want to find out how much has the spring compressed when the child was standing at the end of the board. So this one, you can assume is in equilibrium because the whole object or the whole system isn't moving anymore. So your hinge is right over here. Okay, we apply equilibrium conditions here. Specifically, we apply moments in equilibrium. Okay, so in your case, if you take this hinge as your pivot, what you do know is that when something is in equilibrium, your clockwise moment will be equals to your anti-clockwise moment. So in your case, your hinge being your pivot here, what are the forces present in your system right now and what are the movements that they cause? Your child of weight 40 kg is standing here. He has a weight of say 40 times 9.81. This one is his weight. He will cause a counterclockwise moment about this hinge here. And then after that, when you look at the spring, there's a force at the spring too. Because your diving board is pushing down on the spring will push back up onto your diving board. So there should be a spring force that is directed upwards on your diving board. We are talking about the forces acting on the diving board now. So let's call this spring force F. Okay, it's going to be pointing upwards. And then now, what would be the moment caused by this spring force about your pivot? It will actually cause a clockwise rotation about your pivot. Okay, so these are about the only forces that are acting here. Now you may be thinking, what about the weight of the diving board? In our case, we don't really bother about the weight of the diving board because there's no mention of the weight inside your question. So we can't really proceed with anything on the weight. Okay, so we don't consider the weight of the diving board here. We only consider the two forces here. So if clockwise moment is equal to anti-clockwise moment, we can now say this. But before we can proceed, we need to identify the perpendicular distance. For the 40 Newton, sorry, for the 40 times 9.81 force, the perpendicular distance is 5 meters. For the spring force, the perpendicular distance is actually 2 meters. Okay, So now that you've found out all the forces, say now clockwise moment equals to anti-clockwise moment, you will get F times 2 equals to 40 times 9.81, because this one is your weight. Then you multiply with your perpendicular distance, it will be 5. So your F would actually be some value. Your F would actually be 981 Newton. Okay, it will be 981 Newton. This is first working. Now, second working, you apply Hooke's law. Okay, because you notice they are giving you a spring constant here. So F is equals to Kx. The spring force is 981 Newton. Your spring constant is 10 kilonewton per meter. So it's 10 times 10 power 3 times with x. So your x will be 9.81 times 10 power minus 2 meter. So change to centimeter, you will get 9.81 centimeter. Your answer would be C. Okay, this is for this question. Then you move to question 14. Okay, now question 14, this one is pretty straightforward. Question 14 says that a granite rock at the surface of the Earth has density rho. The rock is transported to the surface of another planet. The acceleration of free fall on the surface of the other planet is twice that on the surface of Earth. What is the density of the rock on the other planet? Okay, so now in our case, when you go from, say, Earth to another different planet, which is not specified, the mass by right should remain constant. The weight will vary since G varies, because weight is equals to mg. So if mass is constant, that would mean that W is directly proportional to G. So in our case, they told you the acceleration of free fall is twice that on the surface of the planet. So on that new planet, if we know that G is 2 times more, the weight must be 2 times more. So weight is twice that on Earth. Okay, that's what we can infer here. But the question isn't really asking you about the weight. The question is really asking you about density, you see. So another thing that you can also kind of say is constant here when you shift your rock from Earth to another different planet is the volume. Volume should remain constant. It won't suddenly expand or it won't suddenly shrink. The volume by right should remain constant for the rock. Okay, so I need to make use of this information and this information to deduce my density. Because you see, density by right is defined as mass over volume. So in my case, I already know mass is constant. Volume is also constant. Therefore, density must be constant. So density remains the same. So my answer should be B here. Okay. There's no change in the density. Common sense will also tell you that density cannot change here in the first place. All right. So this one, let me just write it here. Actually, there's no need to cancel this. This one, volume constant. This one is represented by symbol V. Okay. Okay, then if that is okay, then you move on to question 15. Now in question 15, a closed U-shaped tube contains a stationary liquid of density rho. One side of the tube contains gas at pressure P1 and the other side contains gas at pressure P2 as shown in the diagram below. And then from here, they mentioned that the acceleration of free fall is G. Which equation below here is correct? Okay, now for questions that deal with some sort of manometer or U-tube like this, there's one thing that we will always refer to, that one being this one. Pressure for the same liquid at the same depth or height will always be the same. Okay, so as long as you're referring to the same liquid at the same depth or height, your pressure would always be the same here. So let's just say, for example, I consider this reference depth. This reference depth here has the same liquid at the same depth, right? Correct. So from here, let's just consider this point being point A and this point here being point B. I could actually say that pressure A is the same as pressure B based on the statement above. But pressure at A is caused by the pressure of the gas above it. And then pressure at B is caused by the pressure of the liquid above it plus the pressure of the gas above it. So in my case, I can actually write this one out as this, where I say PA is equals to P1 equals to P of the liquid plus P2. Okay. Now P of the liquid can be rewritten as H rho G. So P1 equals to H rho G plus P2. So what is your H here? Your H is actually this part here. This part here is your H. Okay, maybe I should use a different color. H is actually this part here. Okay, H is actually Y minus Z. You take this length minus this length, you will get H, right? So you will get P1 equals to Y minus Z rho G plus P2. So then eventually you get P1 minus P2 equals to rho G Y minus Z. The answer here would actually be C. Okay, that's for question 15. So then I move on to next one, question 16, or that's below here. So let me clear this one off. For question 16, which product of two quantities is equals to power? So specifically, they want the definition for power here. Power is rate of work done, but work is the product of force times distance moved in the direction of force. So you get something like this. Now, if you regroup the S over T, you're going to get this. The S over T is actually distance over time is actually equals to speed. So therefore, power is the product of force times velocity, which is your answer choice B here. The rest of it is not really relevant. If you're talking about force times distance, this is actually work. Work done times time. This one actually doesn't really relate to anything. Work done times velocity also doesn't relate to anything. So the answer here is just B. Okay. Then if you move on to question 17, question 17 will be talking about some sort of filament lamp. Now, question 17, researchers have developed a new type of filament lamp with an efficiency of 40%. All types of filament lamps have an efficiency of 5%. The two types of lamp produce the same useful output power. So keyword here is same useful output power, same P out. From here, what is the ratio of input power to the new type of lamp to the input power of old type of lamp? So in your case, what you can do is something like this. Now, if you recall the definition of efficiency, efficiency is the ratio of P out to P in. Here they mention same useful output power. That means same P out. So you refer back to this equation here, I can actually say that P out is constant. Therefore, efficiency is inversely proportional to P in, or in other words, P in is actually inversely proportional to the efficiency. So what you want is the ratio of input power of new lamp to old lamp. So you can actually say something like this: P new to PO is actually 1 over N new over 1 over N old. Okay, maybe I write this better. 1 over the new efficiency over 1 over N the old efficiency, which in turn gives me this. N O over N new. So the old efficiency is 5%. Let's just change it to fraction. The new efficiency is 40%. Let's just change it to fraction. Eventually, you will get your answer as 0.125. Round it out to 2SF, it will be 0.13. Your answer would be A. Okay, so that is pretty straightforward. Then you move on to question 18. Question 18 is actually on the derivation of your KE. You need to know the derivation of your KE in order to be able to answer this question. If you read the question, they mention a student attempts to derive the formula for kinetic energy. She begins by considering an object of mass m, which is initially at rest. A constant force F is applied to the object that causes it to accelerate to final velocity v in displacement s. The kinetic energy gained by the object is equal to the work done on the object by force F. Which of the equations here would the student not need in order to derive the formula EK? Which particular equation is actually not used here? So in our case, let's just go through a bit of how kinetic energy was just derived in the first place. So imagine this. You have a block that you try to apply a force of F, a constant force F. So when you apply a force F on this block will start to accelerate. Bearing in mind that your block was actually starting from rest, so this one will be 0 meter per second. So when you apply the force F and it starts to accelerate, it will move through a displacement S, and it will have a final velocity v here. Okay, so this is the situation that's actually being described by your question here. Now, there are a few things that you can actually do from here. You can actually say that the work done in your case is the force applied times the distance moved, but you need to substitute out F, you need to substitute out S. You need to substitute both these things out in the first place. So if you want to substitute out for F, the one thing you can use is this. You can actually say that F is equals to MA here. Okay, so that your case here, yeah, F is equals to MA. Then after that, you can also use your kinematics equation. V squared is equals to U squared plus 2AS. But because this one was starting from rest, it becomes V squared equals to 2AS. Okay, so from here, your AS is actually B squared over 2. Right, you need to make use of these two equations. This one is your kinematics. This one is your F net equals to MA. So now back to the original equation that you have. If you sub in for F, it will become MA times with S. Now you go and rearrange this again. You group AS together, you get MAS, right? So notice you've already found out what is AS here. This one is actually V squared over 2. So M times V squared over 2 will give you this. So therefore, your work done is actually half mv squared. Now, in your case, you will say that work done is equals to the change in your kinetic energy. So it will be half mv squared minus ke minus 0. Now, because when you say change in ke, you're talking about these two. Your ke here is just 0. And then here you have some unknown value of ke lah. You're trying to find this one here at this point. That's why here I put KE just minus 0. So eventually you get KE equals to half mv squared. This is how your kinetic energy equation is actually derived. So from here, you can now see which equation is used, which equation isn't. If you look at the first answer choice, F equals to MA, this one is used. W equals to Fs, that one is used. V squared equals to U squared plus 2AS, this one is also used. So these three have been used. The only one that hasn't been used is this one. E equals to half Fs. It has not been used at all. So your answer here is actually going to be C. Okay. So that one is for this particular question. Okay, then from there, you can then move on to question 19. Now in question 19, they mentioned that a metal wire obeys Hooke's law and has a Young modulus of 2 times 10 power 11 Pascal. This wire has an original length of 1.6 meter and a diameter of 0.48 times 10 power minus 3 meter. What is the spring constant of the wire? Now, spring constant here refers to K, the symbol K, all right? But what they've given you is nothing related to force, nothing related to extension. Instead, they give you Young's modulus, some original length, and then some diameter here. So this one, you need to know how to manipulate your equation a little. Now, if you're given Young's modulus, the first equation that you should come to your mind is this. Young's modulus is the ratio of stress to strain, which is actually force per unit area, and then extension over original length, which in turn will become FL over AE. Okay. Now, in your case, you try to group F over E together because you see, Hooke's law was basically this one, isn't it? F is equals to KE. I replace X as E here, E being my extension, so that K is actually F over E. I'm trying to find out F over E from the first equation here. So here, if you rearrange this, you will get E is equals to F over E times with L over A, which would in turn be equal to K L over A. Okay, so this is what you have. You would be able to find out K now from this particular equation. Yeah, not to forget, your area is actually pi over 4d squared. So this is the final form of your equation. So from here, you just sub in the values that you know. Your Young's modulus is 2 times 10 power 11. Your K is what you want to find. Your original length is 1.6. Then you have pi over 4d squared. Your diameter is 0.48 times 10 power minus 3. Square that value. Eventually, you will get your answer as 2.26 times 10 power 4 Newton per meter. Okay, so in your case, it should be answer choice B. Okay, that's for this particular question. Then move on to question 20. Let me clear this thing up. Okay, now in question 20, a wire is being stretched by a tensile force. Which statement about the elastic limit must be correct? They are asking you about the elastic limit here and for the statement that must be correct. So in the first place, what is elastic limit? Elastic limit, you will have learned it as this. Elastic limit is the point to which deformation remains elastic. Okay, it's the point to which deformation remains elastic. Beyond this point, deformation is plastic. And beyond this point, deformation is plastic. Okay, so you look at the first answer choice where they mentioned to you the deformation is plastic after the elastic limit has been reached. This one seems to be the answer if you refer to what I just wrote here. Then after that, you look at the second answer choice. The deformation is plastic until the elastic limit is reached. This is actually wrong. It should have been the deformation is elastic until the elastic limit is reached. Then after that, you try and double check with answer choices C and D. Answer choices C is saying that the extension is proportional to the tensile force after the elastic limit has been reached. And then in D, they mention the extension is proportional to the tensile force until elastic limit is reached. So what's actually happening here? You just look at the phrase where they say extension is proportional to tensile force. This is actually kind of relating to your Hooke's law. So let me just write some additional statements here. This one, you can actually say this. Force is directly proportional to extension until a point called limit of proportionality. Okay. Hooke's law is obeyed up to this point. Okay. Force being directly proportional to extension, that one only applies until some particular point called limit of proportionality. Okay. Worded another way, Hooke's law is obeyed up to this point. Okay. And another thing that you can also kind of say from here is that limit of proportionality is usually before your elastic limit. So it will probably be better if you just try to look at it from a graph like this. Your typical graph would be something that looks like this. It's a straight line. And then after that, it starts to curve a little. And then after that, it starts to curve a lot. So your limit of proportionality would be here. This is your LOP. Your elastic limit could probably be here. Okay. So up to this point here, force is directly proportional to extension. Hooke's law is still a bit up to this point. Then up to this point here, this one deformation is still elastic. And then after that, it's just going to be plastic. Okay, this one is a diagram that kind of represents whatever information is stated here inside your question. All right, so this is for question 20. Now, then you move on to question 21. Which statement is correct for all types of progressive wave? So, keyword all types of progressive wave. If you look at the first answer statement, the distance from a peak to the next trough is equals to a wavelength. This one is obviously wrong, because if you recall how a wave looks like, it looks like this, isn't it? Where we say to you that there's this wavy pattern. So if they tell you distance from peak to trough is equals to a wavelength, they're actually saying from here to here. So they're saying that this one is actually equals to wavelength. This is obviously wrong. It's actually supposed to be half a wavelength. This is the correct one. If you want to have a complete wavelength, it should be crest to crest. This one is wavelength. This one is the correct one. Okay, so this one is out. It's supposed to be half wavelength. And then after that, progressive waves can be demonstrated in a ripple tank. This one also out. Not all progressive waves can be demonstrated in a ripple tank. Let me just ask you this. Can you demonstrate light waves inside a ripple tank? You can't, right? So light cannot be demonstrated in ripple tank. You can demonstrate water waves, progressive water waves inside a ripple tank, but you cannot demonstrate light. Okay. Light is actually a progressive wave, as you already know. And then after that, answer statement C, they consist of vibrating atoms. Okay, not all progressive waves will consist of vibrating atoms. Another case in point would be EM waves do not involve vibrating atoms. EM waves do not involve vibrating atoms. Okay, so let me just rewrite this properly for you. So EM waves can travel through vacuum and they don't even need atoms to vibrate in the first place. So C is actually out. Now, that will leave you with only answer statement D. They transfer energy from one point to another. This is correct. Okay, because what you learn is that progressive waves have wave profiles that move, and energy that move from one point to another. Okay, progressive waves will have wave profile that move from one point to another. They also have energy that move from one point to another. So here they say they transfer energy from one position to another. This is correct for all progressive waves. Okay, so this is question 21. Okay, so for question 22, you have a transverse water wave that is moving along the surface of some water. This causes the ball to move vertically without moving horizontally as it floats upon the surface. At one instant, the ball is at the position shown. The wave has a frequency of 0.2 Hz and an amplitude of 0.7 meter. The distance between the trough and adjacent pin is 2.4 meter. Now, what would be the distance traveled by the ball in a time of 20 seconds? So the ball that they're talking about is actually this ball right over here. They want to know how much is the total distance that has been traveled. Okay. So one of the things about progressive waves also just now, as a continuation of what I just wrote, I mentioned that progressive waves transfer energy from one point to another, right? That's one of the things that I wrote in the question before. But they do not transfer matter. They do not transfer matter or mass from one point to another. Okay, while you can say progressive waves do transfer energy from one point to another, they do not transfer matter or mass. So in the case here, when you're talking about this ball here, your progressive waves will try to move. It will originally be something like this. This one will be like, say, at t equals to 0. And then at t equals to 1, the wave profile will move. It will probably be something like this. This one will be t equals to 1. And then maybe at t equals to 3, it will be something that looks like this. Okay, this one is the wave profile actually moving with time. So as the wave profile keeps moving with time, this ball here that you see, it will not go along with the wave profile. The wave profile is moving towards another position, but the ball itself will not follow the wave profile. What it will actually just do is that it will just oscillate up and down. If you look at the pink colored arrow that I just draw, pink colored line that I just draw representing t equals to 1, the ball will actually start to move downwards in the next 1 second. And then after that, if you look at the green colored wave profile that I just draw, another 1 second later at t equals to 2 seconds, the ball will actually move further down. So it's actually moving down. And then you try to extrapolate its motion with time, that ball is actually just going to be oscillating up and down. as your wave profile moves. It's just going to be oscillating up and down, but it's not going to be moving to another different position following the wave profile. Okay, so here, the thing that I just want you to realize is this. The ball will just oscillate up and down. When it oscillates up and down, it follows a particular motion that kind of looks like this. It will just go down and then it will just go back up. Now, when it goes from this position and then it goes back to the same position, this is considered to be one cycle for you. Okay, and the period of this oscillation, you can actually find it out from your frequency. So here, frequency is the reciprocal of your, here, period is the reciprocal of your frequency. You get 1 over 0.2, you will get the answer as 5 seconds. So here, for the ball to move from this top position, going down, and then going back up to that same position, representing one cycle, the time taken for that one complete oscillation is 5 seconds. This is actually what the period is. Okay. So now, one thing to note here is, for one cycle, what's the total distance traveled? You see, right now, I can say that when my object, or rather the ball, move downwards like this, the distance traveled is going to be 1.4, because you can see something like this. Maybe it's better if I just draw some arrows. This one will be 0.7, because this one is 0.7. You see the amplitude is 0.7. Then I go down further, it's another 0.7. Then when I go back up, it's another 0.7. I go back up again, it's another 0.7. So in total, I can actually say this. For one cycle, distance move is equals to 4 times 0.7, giving me 2.8 meter. So for the ball to move one full cycle, it would have traveled a distance. You see, the keyword here is distance traveled, not the displacement. Okay, they just want the distance traveled. So distance traveled for one cycle is this. Now the question says, what is the total distance traveled for a time of 20 seconds? So in your case, you try to find out how many number of cycles are there in 20 seconds. So number of cycles, you take the time, 20 seconds, you divide by the time taken for one cycle, which is 5 seconds, you will end up with 4 cycles. So in 20 seconds, your ball would have oscillated 4 cycles. And in one cycle, you know your distance traveled is this. So what is your total distance traveled now? Therefore, your total distance is going to be 4 times 2.8, giving you an answer of 11.2 meters. So the answer is C. Okay, this is the total distance traveled by your ball in 20 seconds. It has 4 cycles inside, and one cycle was 2.8 meters traveled. So you multiply with 4. Okay, so that's for question 22. Okay, now for question 23, this one concerns something else. It's a longitudinal wave. Now, a sound wave travels from left to right across a room. The biaxial distance across the room of the displacement of the air particles at one particular instant is as shown here. Now, at which distance will the air pressure be the lowest? So if they're talking to you about sound wave here, the first thing that you should have noticed is that this one is actually a longitudinal wave. Okay, so specifically when you're talking about longitudinal wave, the oscillation of particles is parallel to wave travel. So if right now you're talking about, say, a sound wave that's traveling across the room like this, let me just draw an arrow here like this. You're talking about sound wave that's traveling across a room from left to right. This is the direction of your wave travel. The air particles along the way of the sound wave will only oscillate left and right parallel to your wave travel. So you expect your air particles to just go left and right in a manner similar to this, parallel to your wave travel. Okay. Now, the graph that you have here is a graph of displacement of your air molecules at a particular instant. So this graph that you have is a displacement distance graph, showing you the displacement of all the individual air particles at one particular instant of time. It could be that maybe say this one is actually at t equals to 1 second. And then these are the displacement of all the particles A, B, C, D, E, F, G at that time. Okay. So in our case, how do you interpret this graph? Now, when it comes to displacement, you guys would have remembered that displacement is actually a vector. So when it comes to vectors, there are directions involved. And when you have directions to consider here, you would have a positive and negative sign. A negative sign just simply means that the direction is opposite. Okay, so here, let's just assume that going towards the right is positive displacement, and then going towards the left is negative displacement. Okay, these are the conventions that we use here. So before we can go to that, there's another thing that you should also remember. Sound waves have points of compression and refractions. Okay, sound waves have points of compression and refraction. Okay, there will be points of compression and refraction when you're talking about sound wave. And then from there, there's something that you can then say compression is highest pressure since the molecules crowd together towards that point. And then refraction is lowest pressure since molecules move away from that point. Okay, and then the other thing that you should know is that compression and refraction is always at the equilibrium. Points of compression and refraction are always at the equilibrium. Okay, points of compression and refraction are always at the equilibrium position. Okay, so in your case, your question asks you to determine the distance at which air pressure will be lowest. You are actually trying to find out the position for your refraction. Where is the position of your refraction? So based on point number 3 that I wrote here, points of compression and refraction will always be at your equilibrium position. You have two choices. Either is B or either is D. Okay, but which of these two is compression, which is refraction in the first place? Now, to see which one is compression and refraction, you have to look at how the particles are being displaced. That's the reason why just now I told you your displacement has a positive and negative sign associated with them. So in our case, we associate particles displacing towards the right as positive displacement, particles displacing towards the left as negative displacement. So in your case, you imagine this now. If this is your particle here at equilibrium, and there are some other particles towards the left-hand side of your equilibrium, as well as right-hand side of your equilibrium like this, maybe I just better draw smaller particles. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so let's just assume that these are your air molecules. if you look at B, you look at the left-hand side of B, these are all positive displacement. This is telling you that all your particles are actually being displaced towards the right-hand side. But if you look at the right side of B, this is negative displacement. This is telling you all your particles are displaced towards the left. So notice that in your case, right over here, the particles are actually crowding towards this point. So this one is actually supposed to be your compression. Since you notice the particles are all actually crowding towards this point. Now, similarly, you can apply your analysis for point D here. If you look at the left-hand side of point D, you already see that it's negative displacement. Your particles are all going to be displaced towards the left. But if you look at the right-hand side of point D, this is positive displacement. That means all your particles are actually being displaced towards the right. So looking at this particle itself, it seems that all the particles are shifting away from it. So this is actually your rarefaction because your particles are shifting away from them. Okay, shifting away from that point. So your answer here should have been D. This is not B. D is your rarefaction point. That is the point where you have lowest pressure. Okay. Then if you're okay with that, then have a look at question 24. You have a source that emits a sound wave of a single frequency. The Doppler effect causes a different frequency of sound to be heard by a stationary observer. What is a requirement for Doppler effect to occur? So what actually is Doppler effect? Doppler effect is just apparent change in observed frequency, apparent change in observed frequency when there is relative motion, when there's relative motion between source and observer. So the key requirement here is that you need to have relative motion between the source and the observer. So you look at the answer statements one by one. A source that is moving as it produces the sound wave, this is actually relating to this one already. So the answer should have been A. So answer choices B, C, D won't really be the correct one. A source that produces polarized sound wave, nope. A source that produces sound wave of changing amplitude, not really. A source that produces sound wave of changing frequency, also not the answer. So B, C, D is out. Only A is correct. Okay. So 24 is done. Then we move on to question 25. Now, in question 25, they mentioned that an electromagnetic wave in free space has a frequency of 2.5 times 10 power 14 Hertz. Which region of the EM spectrum includes this frequency? So this is an EM wave in free space. From here, you can actually say that your V is going to be 3 times 10 power 8. Okay. Electromagnetic waves move with a speed of 3 times 10 power 8 meter per second in vacuum. Free space is actually vacuum right over here. Okay. So you want to find out the spectrum region of the spectrum to which this frequency belongs. If you use equation V is equals to F lambda, your speed is 3 times 10 power 8. Your frequency is 2.5 times 10 power 14 times lambda. Lambda would actually be 1.2 times 10 power minus 6 meter for you. Okay. And then from there, you try to reproduce your EMA spectrum. Just draw a series of vertical lines and then start labeling M from 10 power 3, reduce by 10 power 3 each time. The only exception is between 10 power minus 6 and 10 power minus 9, you have to include 10 power minus 7 here because you have to take into account the wavelength of visible light. So this one is radio waves, microwaves, infrared visible light, ultraviolet, X-ray, and gamma ray. Then going towards the right is where wavelength is decreasing. Okay, so you look at this one, 10 power 6 is the order of magnitude of your wavelength now. 10 power 6 is somewhere around here. It could be visible light, it could be infrared, so you can't really judge from here because you don't see it lying right in the middle. So what you need to do from here then is you try to recall what's the wavelength of visible light. Wavelength of visible light is 400 times 10 power, is 400 to 700 nanometer. If you change it back to meter, it will be 4 to 7 times 10 power minus 7 meter. Okay, so now you can clearly now see which region does this wave actually belong to. You see 10 power 6 meter is actually larger than 10 power minus 7 meter. 10 power 6 is larger than 10 power minus 7. Okay, so in your case, you are really talking about this wave being infrared. Therefore, this wave is infrared. Okay, it's going to be here, not over here. Okay, it will not be on the right hand side, it will be on the left hand side. So your answer here is going to be A. Okay, so that's for this. Then question 26 is on the new portion of your syllabus where it concerns polarization. Okay, so in your case, they mentioned that two polarizing filters are placed next to each other so that their planes are parallel. The first polarizing filter has its transmission axis at an angle of 50 degrees to the vertical. The second polarizing filter has its transmission axis at an angle of 20 degrees to the vertical. From here, the angle between the transmission axis of the two polarizing filters is 30 degrees. A beam of vertically polarized light of intensity 8 watts per meter square is incident normally on the first polarizing filter. What is the intensity of light that's transmitted from the second polarizing filter? Okay, so this one would probably be best understood if you're trying to draw out the diagram. Okay, for example, this is your first polarizer. I'm trying to draw it as best as I can. This is your first polarizer. Okay, maybe I try to draw it at an angle so that it's easier. This one is your first polarizer. Then this one is your second polarizer. Okay, so first polarizer, second polarizer. Now your first polarizer is at an angle of 50 degrees to the vertical. So that means something like this. If this one is your vertical, your transmission axis is 50 degrees from the vertical here. And then your second polarizer is at the angle of 20 degrees to the vertical, meaning to say it is somewhere like this, 20 degrees. Okay, so the angle between the transmission axis of your two polarizers in the first place was 30 degrees, meaning to say you compare the angle difference between the transmission axis of first and second polarizer, it is actually somewhere like this. There's an angle of 30 degrees between them, where this one was for the first one, sorry, where this one is actually the second transmission axis. This is the first transmission axis. Okay, so here the questions mentions this. You have a vertically polarized light of this intensity that was incident normally on the first polarizing filter. So you imagine right now you have a vertically polarized light like this of intensity I naught. This one is vertically polarized, meaning to say your waves are oscillating vertically right now as it passes through this polarizer. So after the polarized light passes through your first polarizer, it will emerge from it, but it will be oscillating at 50 degrees from vertical. Okay, and it will also have a certain intensity I. You are interested to find out what is this intensity I before it hits the second polarizer. So to do this, you will need to make use of Malus law. Malus law is something that you learn from polarization, where we tell you is I equals to I naught cos squared theta. Now the theta here is something that you need to be very careful about. The theta is actually the angle between the polarized light and transmission axis. The angle between your polarized light as well as your transmission axis. So in my case, if I apply I naught, I equals to I naught cos squared theta here for the first polarizer, it will be something like this. This one is I1 equals to I naught cos squared theta 1. Let's call this I1 after emerging from the first polarizer. So it will be 8. I naught is 8 here. Then cos 50 squared. Cos square 50. Okay, the angle between my polarized light and my transmission axis is strictly speaking just 50 here. Okay, so my I1 is actually going to be 5.31 watts per meter square. Okay, so let me just write this closer here. Okay, so this I1 will now go to my second polarizer. I will still need to apply Malus law here, but be careful about the angle theta that you use. Just like I mentioned to you, your angle is actually the angle between the polarized light and your transmission axis. Your polarized light that emerges from your first polarizer is now 50 degrees from the vertical. Okay, and then your transmission axis now is 20 degrees from the vertical. What's the angle between them? The angle between them is actually 30 degrees. So you will have to use angle of 30 degrees here. So in my case, after the light passes through my second polarizer, it will emerge out with an intensity I2. I'm interested in the intensity I2 now. So I2 is equals to I1 cos theta 2 square. I1 was 5.31 cos 30 degrees square. I2 will eventually be 2.48 watts per meter square. So the answer is actually going to be B. All right, this is answer B. Yeah, for the light that emerged from the second polarizer, it will emerge out with this intensity I2, and then the direction of its oscillation will be 20 degrees from vertical. Okay, the direction of its oscillation will be 20 degrees from vertical. It follows the orientation of your transmission axis. Okay, so this is for question 26. Then I move on to 27, which is your stationary wave. Okay, now in question 27, a stationary wave is on a stretch string set up between 2 points P and T here. Which statement about the stationary wave is correct? If you look at statement A, point R is at the node, this one is wrong. This one is supposed to be anti-node. In the first place, node has no vibration. Okay, because you see R here is showing that the point has vibrated. So this one definitely cannot be my node in the first place. Okay, so it cannot be a node. Instead, it actually is your anti-node because it's right in the middle here. And then after that, you look at answer statement B, points Q and S vibrate in phase. This one is kind of correct because you see, what you can see here is that points in adjacent loops vibrate 180 degrees out of phase. Points in adjacent loops, okay? But points in alternating loops, vibrate in phase, okay? If you're talking about adjacent loops, this one is what we call your adjacent loops. This is adjacent loops, this one and this one. But you're talking about alternating loops, it will be this one and this one. This is what we call your alternating loops. So points P and Q vibrate in phase. This one is correct because you see they are in alternating loops. So B is the answer here. But you can also check with the rest of the answer statements. Distance P and T is 3 wavelengths. This one is definitely not correct because what you do know is that distance between adjacent nodes is half a wavelength. So from here, this one is lambda over 2, this one is lambda over 2, this one is also lambda over 2. So distance PT is supposed to be 3 half wavelengths. If they say 3 wavelengths, this is wrong. So this one is supposed to be 3 half wavelengths. Okay. And then the last answer statement where they say that the wave transfers energy from P to T, this one is also wrong. We're not talking about a progressive wave here, we're talking about stationary wave. So stationary waves do not transfer energy. They don't transfer energy, unlike progressive waves. So D is also out. So the only correct answer here is actually B. Okay, so this is for this. Then you move on to question 28. Now for question 28, you have a bar that vibrates with frequency F to produce water waves in the ripple tank. The waves pass through a gap of width X in the barrier so that diffraction occurs. Which combination of vibration frequency and gap width will produce the smallest angle of diffraction? Over here, you're interested in the diffraction that occurs when a wave passes through a gap width, specifically the one that gives you the smallest angle of diffraction, or in other words, the least amount of diffraction. Now, you would have learned before this that significant diffraction occurs when gap width is comparable to wavelength. What this means is that the gap width and wavelength must be similar in size. You can think of it as being the order of magnitude being similar or having same power of 10. All right. So there's a ratio that we can often use in order to determine the amount of diffraction. The ratio of wavelength to gap width is a measure of amount of diffraction. The gap width here, let's call it W, and then your wavelength here is lambda. What we can say from here is that when the ratio increases, your diffraction increases. So the converse will also be true. When your ratio is small, your diffraction is going to be small. We are more interested in this ratio now. When the ratio is small, the diffraction amount is going to be small, giving us a small angle of diffraction. But when you look at your current question here, there are some differences to take note of. there is no mention of wavelength. Instead, they mention frequency. And then your gap width here, rather than it being written as W, is actually written as X. So we'll change our ratio accordingly in order to match the question. So the first thing that we can say about the frequency and wavelength is this. V is equals to F lambda. If V is constant, that would mean that frequency is inversely proportional to your wavelength. Okay. And then the gap width is actually equals to X. So now if we put in what we've done into the ratio was originally wavelength to gap width. So we put in what we've just done, the ratio should actually be proportional to 1 over frequency X. So here we can say this. If you want the ratio to be as small as possible, the fx must be as big as possible. Okay, this is what we want to use in our current question. We want to find the product of fx. The bigger the amount, the smaller our ratio, so the smaller our diffraction. Okay, because this relates to what we have done right over here. Let's just list out the value of fx right next to the table here. For the first row, we have f over 2 times x over 2. We will get fx over 4. And then for the second row, we have f over 2 times 2x. This will give us fx. For the third row, we have 2f times x over 2. This again will give us fx. For the last row, we have 2f times 2x. This will give us 4fx. We want to look at the value of fx, which is the largest. So it should be this one. This one, where fx is the largest, will give us the smallest ratio. Therefore, our diffraction will be the least. The answer is supposed to be D. Now, for question 29, you have an outdoor concert that has 2 large speakers beside the stage for broadcasting music. In order to test the speakers, they are made to emit sound of the same wavelength and the same amplitude. The curved lines in the diagram represents the wavefronts. Where would be the louder sound heard? So we have sound waves of same wavelength and same amplitude right now, and your diagram here is saying that the curved lines are your wavefronts. Your wavefronts are actually your wave crests, okay? And you specifically want the point where you hear the louder sound. So this one will actually relate to interference, specifically constructive and destructive interference. Let's just review a little about those two. When you're talking about constructive interference, the waves must meet in phase, okay? So let me just write it out here. The waves meet in phase. Now, when you have waves meeting in phase, it just means this. Crest meets crest and trough meets trough. It'll be easier to see if you have some sort of diagram to refer to. So let's just imagine that you have 2 waves like this. The waves have these waveforms like so. This is an example of waves meeting in phase, because you can see that the crest is meeting the crest, and then the trough is actually meeting the trough. So when they combine together, you will get a resultant wave whose amplitude is the biggest. You will get something like this. So let me just draw it out. This is your resultant wave now. It is having a bigger amplitude. So this one gives you resultant wave with bigger or biggest amplitude. Okay. Now it is at this point here that you will hear your louder sound. Okay, this is the one that gives you your loudest sound. May concern sound wave, because this is the wave with the largest amplitude. So obviously this will be the loudest sound. Okay. Then after that, if you look at destructive interference is something like this. Let me just write it out. For destructive interference, the waves must meet out of phase, specifically 180 degrees out of phase. So here, waves meet 180 degrees out of phase. Okay, so this essentially means crest meets trough and trough meets crest. So you expect to see something like this. Let me just redraw the waves. I have to draw it smaller here. This one is one waveform, and then this one is another waveform. So in our case, they combine together. What is the resultant wave that you get? Now in your case, you can see that the crest is meeting the trough, and then the trough is meeting the crest. So the resultant wave that you get, provided they are of the same amplitude, would be something like this. You will get nothing. This is your resultant wave. Okay, so this one is going to be resultant wave with lowest amplitude. Okay, it's the direct opposite of constructive interference. Constructive interference gives you the biggest amplitude, whereas destructive interference gives you the lowest amplitude. If the amplitudes are the same, you will actually get zero amplitude. Okay, so you apply this for the case of a sound wave. Destructive interference is where you usually hear the softer sound or zero sound. Okay, zero sound is when the amplitudes are the same in the first place. All right, here the question already did tell you they're of the same amplitude. So by right, you should be getting zero sound. Okay, because they completely cancel off. But if the amplitudes are not the same, the waves won't completely cancel off. You will still get some sort of residual amplitude, say maybe something like this. This one will give you the softer sound. Okay, so back to this question here. They want you to find the point where the loudest sound is heard. From what I've just discussed with you, this one you should know by now should be the point of constructive interference. Okay, you want to find the point where constructive interference is occurring here. But how do you determine that from your diagram? It was already mentioned to you that the curved lines are your wave fronts, or in other words, your wave crest. So here, what you want to do is you want to find the point where the lines meet. Because it's at this point where the lines meet that crest meets crest. Therefore, it will be constructive. If you look at the diagram, do you notice any of the lines meeting or crossing each other? There's only one point that's doing that. That is point D. Over here, you have this line crossing over with this line at this particular point. So this is the point where a crest meets with a crest, thereby giving you constructive interference. You will get a loud sound right over here. Answer choices A, B, and C would not be the answer because you do not notice any of the lines crossing each other. Those are not the points where crest meets crest. Those are not the points where you get constructive. So you will not get louder sound there. It is only at point D itself. Now, before I move on to the next question, let me just explain a bit more about this question. What if the question was changed and they ask you to find the point where you have the softest sound or zero sound? So here would mean that you need to find the point of destructive interference. Would you be able to determine it from this diagram? You can actually do so. Remember that they told you the lines here represent your wavefronts, or in other words, your crest. So I can actually say that this line and this line are my crest. Now you imagine there's another line in between these two lines right over here. That one will actually be your wave trough. So you want to find a point where crest meets with a trough so that you get destructive, so that you get zero sound or softer sound. Those points will actually be points A and B here. If you look at point A, you will notice that there's this one line here, and then it will meet with another line in between the lines. This one is your crest meeting with a trough over at this particular point. So this part is going to be destructive. Now the same could also be said for point B, where you will see that there's this line here that meets with another separate line in between the other existing lines. This is where again you get a crest that meets with a trough. So you will get destructive interference here too. So these 2 points will be where you will get the softest sound or zero sound. Okay. And then if you have a look at question 13, in question 30, you have the equation lambda equals to d sine theta over n is used to calculate the wavelength lambda of light in an experiment that uses a diffraction grating. The light from the diffraction grating is displayed on the screen. What do the symbols n and d represent? So this one, the original form should be d sine theta equals to n lambda for diffraction grating. So n here, you by now should know is talking about your diffraction order, or rather the order of intensity maximum. This is order of intensity maximum. Then your d is supposed to be the distance between slits. Because your diffraction grating looks like this with many different lines, your d is actually the distance between the slits, between adjacent slits. So C is your answer here. N is the order intensity maximum. D is the distance between adjacent slits inside your grating. Okay, so this is for question 30. So if you're okay with that, then let me just go on to question 31. Okay, now question 31. The diagram shows you a block of metal. The block has sides of length ABC as shown, and its volume is V. Each charge carrier has a charge of negative Q, and the number density of the charge carriers inside the metal is N. It takes each charge carrier an average time of T to pass through the block. What is the expression for the current I here? Okay, now this one, when you see mention of number density and current, the first thing that should come to your mind is this equation. I is equals to ANQV. Okay, so there are certain things here to note. When you're talking about this A here, this one is actually the area perpendicular to current flow. Okay, so your current is flowing in this manner here, like this. The area perpendicular to your current flow would actually be this area right over here. It's actually the product of A times C. Okay, and then the other thing to note is this one. This one is actually the drift speed. This one is actually speed, which is actually distance over time. So in your case, if you relate this to your diagram, this should actually be B over T, because your electrons or whatsoever will be going like this, in this manner. Your charge carriers will be going in this manner. It will travel this length B in a time of T. So taking that distance B divided by T will give you your drift speed. So now what you just need to do is you sub in these two information inside. You can actually say that I is equals to AC times N times Q times with B over T. Okay, times with B over T. And then from there, you will be able to do something like this, where you say this one is NQ ABC over T. Now, ABC is basically you multiplying all the three sides here together. This one will actually give you your volume. Okay, so therefore, I is NQ times volume divided by T. Okay, so bear in mind that there are two V's here. This V here is for speed, this V here is for volume. Don't confuse the two symbols. Okay, so your answer here is actually B. Okay, for question 31. So you're okay with that? Then I move on to question 32. Okay, question 32 will be this one. All right, then next one, question 32. Question 32 is this. The circuit diagram shows two lamps X and Y, each connected to a cell. The current in lamp X is 0.5 amps and its resistance is 9.6 amps, 9.6 ohms, sorry. The current in lamp Y is 3 amps and its resistance is 1.2 ohms. What will be the ratio of the power in lamp X to lamp Y? Okay, so this one is pretty straightforward. If they ask you for power right now, the equations that come to mind is P equals to VI, I squared R, and V squared over R. Okay, but here you notice they've already given you current and resistance. So obviously the first one you don't use, third one you don't use, you use the second one. Second one has everything listed out. So in your case, if you want to use P is equals to I squared R, the ratio of Px to Py will be the current of X squared times with its resistance of 9.6 divided with the current of Y squared times with its resistance of 1.2 ohms. You will eventually get your answer as 0.22. So this is your answer, A. Okay, so that one is all right. Then you move on to question 33. Now in question 33, the intensity of light incident on a LDR is increased. The temperature of a thermistor is increased. In each case, the current in the component is maintained at a constant value. So regardless of what happens to your LDR or thermistor here, current is maintained constant. So here, what happens to the PD across each component? So when you're talking about LDR and thermistor, some of the things you will have learned is this. For thermistor, the resistance of your thermistor with respect to temperature would look something like this, where we tell you that as temperature increase, resistance of thermistor drops, and vice versa. Okay, and then when it comes to your LDR, if you look at the variation of your LDR resistance with intensity of light, not current. I here stands for intensity, not current, all right? So it will also follow the same graph shape. In our case here, we say that as intensity increase, resistance of your LDR decreases and vice versa. Okay. So now they want you to find out what happens to the potential difference across each of these components provided that current is constant. So say for example, this one is your thermistor. This is your thermistor. And then this one is your LDR. you're supposed to have a current running through both of them, like this. Current I running through both of them, but they say the current remains constant throughout. So if you apply equation V equals to IR, I is constant here, that will mean that the PD is just proportional to the resistance. So in your case, for LDR, because your intensity is increased, resistance of LDR would drop. Therefore, PD across your LDR drops. This is number one. For number two, for thermistor, they told you your temperature is increased. Temperature is increased, so the resistance of your thermistor would drop. Therefore, the PD across your thermistor would drop. So in your case, PD across LDR drops, PD across thermistor drops. So answer is actually going to be D. Okay, your answer is D right over here. That's for this particular case. Then after that, you have one last question here. I'll finish off question 34 before we call it a day. Now, if you look at question 34, you have an iron wire of length 8 meter and diameter of 0.5 millimeter. This wire has resistance R. Second iron wire has length 2 meter and diameter 1 millimeter. What is the resistance of the second wire? So this one here, because you have mentioned of length and resistance, the first thing you will use is actually R equals to rho L over A. And because they mentioned the diameter here, you can actually expand out the error as pi over 4d squared. Now notice that they're made of the same material. They're both made of iron. So rho is constant. The resistivity is constant. Therefore, resistance is proportional to length over diameter squared. Okay. Then here you can do your ratios where you say that R2 to R1 is the same as L2 to L1 times D1 square over D2 square. So from here you can just sub in your values. L2 is actually 2, L1 is actually 8, and then D1, diameter of 1 is 0.5 square, diameter 2 is just 1.0 square. Now, both are in millimeter here. I actually didn't bother to change them to meter because you see, if I have millimeter here, they cancel off. Even if I bother to change it to meter, they will still cancel each other off. So it doesn't make me any sense to change to meter. You can just leave the units as it is because they cancel each other off. Okay. So once you've done this, you will calculate out the final ratio as 1 over 16. Okay. R2 to R1 is 1 over 16. So R2 is R1 divided by 16, but R1 is actually just R itself. So it will be R over 16. The answer for this is A. Okay. Now, this one is you substituting the value and looking at it like that. There was a so-called easy way that I mentioned to you that you guys could have used. So that one is this. If I already know R is proportional to L over D squared, if I just say for second wire alone, I know that the length of the second wire, you see, is 2 meters for the second wire, but 8 meters for the first wire. So here I can actually say that for the second wire, the length has actually decreased by 4 times. Therefore, R would decrease by 4 times. And then now, if I look at the diameter of the second wire is 1 millimeter, the diameter of the first wire is 0.5. Diameter of the second wire is twice that of the first one. So here I can say diameter of the second wire is doubled. Therefore, my resistance would reduce by 4 times too, because you see, it has an inverse relation with my resistance. If D increase, R will drop. But because it's squared, the effect is squared too. So 2 times 2 will give me 4. the resistance reduces by 4 times. So from here, reduce 4 times, you say overall R reduces by 16 times. Therefore, R2 is R1 divided by 16. Your will be R over 16. This is also another different method that you can use. Okay, so that's for question 34. In question 35, we have a cell with constant electromotive force EMF that's connected across a fixed resistor. Over time, the internal resistance of the cell increases. What change occurs as the internal resistance of the cell increases? Now, it will be good to draw out the circuit here. We have a cell with EMF E connected to internal resistance small r, which is in turn connected to a fixed resistor big R. So this is how our circuit looks like right now. EMF E, internal resistance small r, and then fixed resistance big R. So as it is, if you connect the circuit, you ought to have current that flows through the circuit in this manner here. Okay, so here, what are the changes that could occur if it was mentioned that the internal resistance of the cell is increasing? So right now, we have internal resistance increasing with time. Now, the first thing that we can probably say here is this. When our internal resistance increases, our total resistance will increase. Therefore, our current flowing through the circuit will actually drop. This is number one. And then after that, in our case, the charge carrier is electron. Therefore, the charge Q is fixed. All right. The charge carrier in our circuit right now is usually our electron. There's no other kind of charge carriers. So the Q here is fixed. It is actually the charge of the electron, 1.6 times 10 power minus 19 coulomb. Then after that, if you look at the expression for current, where we say is rate of flow of charge, this big Q here represents total charge. Okay. So if we expand this expression further, we will get I is equals to NQ over T. All right. So from the point above, if we say that Q, the charge of our charge carrier, is fixed or constant here, that would mean that I is directly proportional to N over T. This N over T that we have is actually our number of charge carriers per unit time. Okay, so in our case, if we already know that our current is dropping, that would mean that our number of charge carriers per unit time will be dropping too. Okay, so that is point number 3. And then for point number 4, if you look at the fixed resistor, the power dissipated by the fixed resistor can be given by P equals to I squared R. Now, the resistance of the fixed resistor should be fixed or constant here. So R is constant, P is directly proportional to current square. Now, since we already know that the current is dropping, our power dissipated in the fixed resistor ought to be dropping too. Okay. And then next, we want to look at the fixed resistor and the internal resistor here. If you apply equation V is equals to IR, this is what you will see. This is point number 5. Applying V is equals to IR to the fixed and internal resistor or internal resistance, you will get V is equals to IR. And now, if you look at the fixed resistance and the internal resistance, because both of them are connected in series, no matter what current changes occur in the circuit, it will always be the same current flowing through both resistances. Okay, so now if you were to apply equation V is equals to IR to both resistances, just give me a moment to write it down. Applying V is equals to IR to both fixed and internal resistance, this is what we would expect to see. P is equals to IR, the current being constant through both resistances. That will mean that the PD across them is directly proportional to their resistance. So when you look at the internal resistance is increasing. Therefore, the PD across the internal resistance will increase. There is actually more voltage loss here. Okay. Then next, if you apply Kirchhoff's second law in your circuit here, according to Kirchhoff's second law, applied to this loop right over here, you can actually say that the EMF E is equals to the PD across the fixed resistor plus the PD across the internal resistance. Now, our EMF E is fixed. And then we already determined from above that the PD across the internal resistance is increasing. There's more voltage loss. So what should be the PD across the fixed resistor then? It should actually be decreasing, so that when it adds up with your voltage loss, you're getting back the same EMF. Okay. So for here, what we can say is that if your voltage loss is increasing, the voltage across your fixed resistor will be dropping. Okay. Now, what if you're interested to find the PD across the cell itself? You can imagine yourself as connecting a voltmeter across your cell like this now. If you were to apply Kirchhoff's second law for this particular loop, what you will be able to say then is something like this. Your EMF E is equal to your voltmeter reading plus the voltage across your internal resistance, such that your voltmeter reading will be EMF minus the voltage loss. So in your case, if your EMF is fixed and your voltage loss is already known to increase, what will happen to your voltmeter measurement? Your voltmeter measurement would decrease here, because right now you're having a fixed value subtracting a larger value. So whatever remains would definitely be smaller. So in your case, you can actually say that the PD across the cell decreases. In other words, the terminal PD decreases. Okay, so with all this done, let's just look at the answer choices. Now, in statement A, a decrease in charge of each carrier will occur when the internal resistance of your cell increases. So here, just now we already mentioned that your charge carrier is really just your electron, and the charge is going to be fixed. You saying that the charge is decreasing here for each of the charge carrier would not be correct. And then if you look at statement B, a decrease in potential difference measured across the cell, this is actually referring to the terminal PD. So we already established here that the terminal PD is decreasing. So it will be correct to say that there's a decrease in potential difference across the cell. This one should be the correct answer. Okay, but let's confirm with the rest of the answer choices. And then in statement C, you have an increase in the energy dissipated per unit time in the fixed resistor. When they tell you the energy dissipated per unit time, this is actually referring to the power dissipated. So we already established here that the power dissipated will actually decrease when your internal resistance of the cell increases. So this is actually wrong. And then the last one would be you saying that there is an increase in the number of charge carriers leaving the cell per unit time. So number of charge carriers per unit time, that one is already answered right over here, where we already established as the current is dropping, our number of charge carriers per unit time would be decreasing. So this one is also wrong. The only correct answer would be B. Okay, so that's it for this question. In question 36, Kirchhoff's first and second laws are consequences of the conservation of different quantities. What are those quantities? So try to recall what we remember from Kirchhoff's first and second law. Kirchhoff's first law tells you that the sum of current into a junction is equal to the sum of current out of the junction. It is based on the principle of conservation of charge. And then when you talk about Kirchhoff's second law, Kirchhoff's second law states that the sum of EMF is equals to the sum of PD in a closed circuit loop. This is based on the principle of conservation of energy. So which answer would be the correct one here? It will actually be A. Kirchhoff's first law based on charge, Kirchhoff's second law based on energy. All right. For question 37, you have a potentiometer circuit that is used to determine the EMF EX of a cell. The circuit includes a second cell of known EMF E0 and negligible internal resistance, and a uniform resistance wire PQ of known length. EX is less than E0, and the movable contact J can be positioned anywhere along the length of the resistance wire. Which circuit is suitable for determining EX? Now, let's just have a look at how a typical potentiometer circuit actually looks like. So, a typical potentiometer circuit looks like this. I'll draw it on the left-hand side of your screen here. You would have what you call a driving cell, which is in turn connected to a uniform resistance wire. Okay, so you're trying to measure an EMF now. The EMF will be connected to the bottom of your circuit. And then after that, there will be a connection called your movable jockey right over here. So along the path of your movable jockey, you would have to put a galvanometer so that you would know when you have reached balance length. So there are a few characteristics to this potentiometer in order for it to work properly. Okay. Now, if you look at the driving cell, there's an EMF there. We will call this the driving EMF. And then for the EMF that's being measured, we'll call this the EMF being tested. Now, for your potentiometer to work properly, your driving EMF must be more than the EMF being tested. Okay. And then the second thing you should know is that your battery terminals or cell terminals must match for a potentiometer. Meaning to say, if this is positive, this one must be positive. This one is negative, this one must be negative. So that's what I meant by the cell terminals must match. So let me write it down here. The cell terminals must match. This means that positive matches positive, negative matches negative. All right, this is the second point to note. And then the last thing to note would be something that I've just mentioned. Your galvanometer must be along the jockey connection. Okay, these are the three main characteristics. As long as you know these three, you'll be able to answer this question here. So let's look at the answer choices one by one. Now, answer choice A would be unsuitable, namely because the cell terminals do not match. Because you can see over here, this is positive, but this is negative. This is negative, but this is positive. So this one is not suitable. And then after that, if you look at answer choice B, answer choice B would also not be suitable. Okay. Now, if you look closely at the EMFs that were put there, your EX, which is the unknown EMF, is now used as driving cell. This is actually wrong. It should be a known EMF that is used as a driving cell. And then after that, you can see over here, your known EMF is being measured. So they got the EMFs the other way around. Okay, it should be switched. so that your potentiometer can work properly. So B is out. Then if you look at answer choice C would also be wrong, namely because you can see your galvanometer being put here. So here, your galvanometer is not along the jockey connection. So it's going to be wrong. So the only answer here would have been D. So you can check it one by one. Your cell terminals are aligned, positive, positive here, negative, negative here. Your galvanometer is along the jockey connection. And then after that, you can see here that your EMF being tested is this one. This one is the unknown EMF being tested. And then this one is the known EMF used as driving cell. And at the same time, we also can see that E0 is more than your EX. This one is already stated at this part of your question here. Just now it was already mentioned to you that your driving EMF must be more than your EMF being tested. So answer choice D satisfies all the requirements. It should be the correct answer. All right. Now for question 38, in an experiment on alpha particle scattering, alpha particles are directed on a thin gold foil. Most of the alpha particles pass straight through the foil or are deflected by small angles. A small number of alpha particles are deflected by large angles. What cannot be deduced from this experiment? So you're supposed to pick out the false statement here. There are usually two observations that can be obtained from the alpha particle scattering experiment. The first one being that most alpha particles pass straight through the foil or are deflected by small angles. This is the first observation. And then the second observation is that a small number are actually deflected by large angles. This is the second observation. So from these two observations, there are three main conclusions that you can actually get. So the first one being most alpha particles pass straight through the foil. The conclusion that you will be able to get from this is that the atom is mostly empty space. This is the first conclusion. And then the second observation that you would have seen is that a small minority or a small number of alpha particles are deflected by large angles, more than 90 degrees. So there are two conclusions that you can actually get from that. The first one being the nucleus is positively charged, and then the second one being that mass of atom is concentrated in the nucleus. So these are the three main conclusions that you will usually get from alpha particle scattering experiment. So you are supposed to see from the answer statements which is actually not within these three. So let's look at the answer statement one by one. The atoms are mostly empty space for A. This is actually correct. And then most of the mass of an atom is concentrated in the nucleus. This is also correct. And then for C, where they say the nucleus of an atom contains protons, this one doesn't seem to relate to what we've just discussed, so we'll just leave it first, and then we look at answer statement D. So for answer statement D, they mentioned that the nucleus of an atom is small compared to the size of an atom. This is actually related to points A as well as B. So you can actually say that D is also correct. So the only correct, or rather incorrect statement here is actually C, where they say the nucleus of an atom contains protons. This is actually something that we never found out from the results of your alpha particle scattering experiment. There's nothing from the experiment that tells us that the nucleus has protons. We only knew that the nucleus was positively charged. But where did that positive charge come from? We do not know. Okay, so that one will have been found from another different experiment. For question 39, you have 4 nuclei that are represented below. Which statement about this nuclei is correct? For A, you have an uncharged atom of element Q that has 24 orbital electrons. So this one is an uncharged atom. What do we know about uncharged atoms? So I'll just write it right over here on the right hand side. If you have an uncharged atom, this typically means that the number of protons is equal to the number of electrons. Okay, so if they are asking you to refer to element Q now, element Q is actually 24, 13. So you look at the proton number. Proton number will give you an idea of how many protons there are for the atom. In your case, you have 13 protons. You ought to have 13 electrons in order for your atom to be uncharged or neutral. So here they say you must have 24 orbital electrons. This is actually false. Okay. Then if you look at B, B says that nuclei G and M are isotopes of the same element. So let's just review what is an isotope in the first place. If you recall what an isotope is, isotopes have same proton number but different nucleon number. So if you're asked to compare between nuclei G and M, we know that G is actually 2515 and then M is actually 2512. So you just look at the proton number themselves, these are actually different, therefore not isotopes. So B is also going to be out. Now, then you now look at answer statement C. When E absorbs a neutron and then emits an alpha particle, E transforms into M. For this one, it's pretty straightforward. You just write out the nuclear equation. So you have E 2814. Let me write this properly. E2814. It absorbs a neutron, so it should be on the left hand side here. It absorbs a neutron, 0, 1. And then after that, it will transform into element M. So let's just call this unknown element X first. And then it emits an alpha particle, alpha 42 here. So let's just find out what is the proton number and nucleon number of this unknown element X. Now, if you apply principle of conservation of proton number and nucleon number for your nuclear equation here, you can actually already see that this one is 14 for the proton number. So by right, your proton number after the reaction should also be 14. So this one should have been 12. 12 plus 2 will give you 4. And then if you look at the nucleon number at the top, this one is 29. So after the reaction, it should also have been 29. So X here for the nucleon number should have been 25. So that when you plus with 4 here, you will get back 29. So this element X that you're looking at here is having a nucleon number of 25 and proton number of 12. Is this element M? Yes, this is actually the same as element M, because you can see right over here, it has nucleon number of 25 and proton number of 12. So the correct answer here should have been C. C would be the correct answer here. But again, let's double check with the last answer. When M emits a beta minus particle, M transforms into cube. So this one, we can actually try and rewrite it out, another nuclear equation, just to double confirm. So what we have is your M2512. Let me write this again. M2512 emits a beta minus particle, and then M transforms into cube. So let's call this unknown element Y here. And then a beta minus particle is emitted. So it's the same thing as before. We try to apply conservation of proton number and nucleon number. So since this one is 12, we know this one must be 12 when it comes to the proton number. So this must be 13 then. So that 13 plus with minus 1 gives you back 12. And then when you look at the nucleon number of 25, after the reaction, it should still be 25. So in your case, the beta minus particle has 0 nucleon number, so the unknown element Y must be 25. So now, is this unknown element Y the same as element Q? Element Q is 24, 13. The nucleon numbers are actually different, so you cannot say that they are the same here. Okay, so D is also out. Now, for the last question, 40, a neutron is composed of 1 up quark and 2 down quarks. When a neutron decays to a proton, a beta particle is emitted. What is the change in the quark structure of the neutron due to the emission of the beta particle? The symbol for a neutrino is Be, and for an antineutrino is Be bar. Your current question never really mentioned to you whether it's a beta plus or beta minus particle, but from the other information given, where you saw that a neutron is becoming a proton, is decaying to become a proton, it should rightly be a beta minus decay. So when it comes to beta minus decay, we know that a neutron changes to a proton, and you have your beta minus particle plus your electron antineutrino. So let's just fill in the proton number and nucleon number here. So this one will be 0, 1, 1, 1. This is negative 1, 0 for beta minus particle. And then your electron antineutrino does not have any proton number or nucleon number. When you look at the quark composition of your neutron and proton, your neutron is up, down, down. Proton is up, up, down. Your quarks are actually changing from 1 down quark to an up quark. Okay. So a down quark changes to an up quark, and then you have the emission of your beta minus particle and your electron antineutrino. So your answer here should rightly be B, where they've stated here down quark becomes an up quark plus your beta minus particle plus your electron antineutrino. So this is the last question for this paper.